It's just a science project.
Silent breed is people!
A doctor friend once said the same thing to me. Frankenstein was his name.
It's alive! It's alive! It's alive!
That sounds like something out of science fiction.
Please explain to me the scientific nature of the whammy.
We live in a spaceship, dear. So?
Yes, science!
Program complete. Enter when ready.
Hello and welcome to episode 239 of Science on Top, the Sunday, the 21st of August 2016. I'm Ed Brown and I'm joined by Dr. Shane Joseph and Lucas Randall.
Howdy.
Okay, so this show has a fair bit of ancient history in it. So let's start off by talking about the supervolcanoes 100 million years ago. Lucas, these were really powerful eruptions that threw rocks literally from one coast of Australia all the way to the other coast, a distance of about 2,500 kilometres. That's one hell of an eruption.
Yeah, absolutely, and it's kind of like talk about your massive hissy fit. Obviously, supervolcanoes are one of the Earth's coolest things. I think it's long been a topic that I think most children go through this phase of. They do dinosaurs, then they do volcanoes, and then hopefully they do space. These are parts of the essential steps to being an adult, learning these things. Yeah, am I right?
Absolutely. That's the path I went through. and I'm still going through.
Still going, and I don't think any of us ever really get beyond any of them either. But supervolcanoes are awesome. They're just as the name implies. It's just like a regular volcano, but big. And one of the things about supervolcanoes is they don't erupt in the typical fashion that you associate with a volcano. You tend to see, and you think of the stereotypical volcano, which tend to be, you have a nice sort of, volcano-shaped hill with a caldera, a crater in it, and it's spewing lava and it's gently trickling down the sides. But there's lots of different types of volcanoes. There's shield volcanoes, like the one on Mars, for example, like Olympus Mons. These things are massively high potentially, but they're also got a really broad base, so they don't really look like a volcano. There's other volcanoes that are, of this supervolcano type, which tend to form at the top of these plumes, these areas where the magma chamber is quite close to the surface, and it goes really, really deep, and they just hold a huge amount of magma in them. So, of course, there's a very famous one over in the US in one of the parks over there. Which one are we talking about, guys? The
Yellowstone National Park.
I love seeing all of the...
I passed the test.
Yeah, I love seeing all the documentaries about supervolcanoes, because they always throw in Yellowstone, and it will kill us all any minute.
Any minute now.
Any minute. So hopefully Beetlejuice goes first, so at least we get to see that before Yellowstone goes off, because we probably won't be seeing much of the aftermath of Yellowstone. But one of the things about Yellowstone is it's such a huge supervolcano that it will pretty much, it'll destroy the chemistry of our atmosphere, it'll cause massive climate change, it will throw sort of pumice all over the earth, and just other various things that just will ruin your day. Not good.
Not to mention your entire race and species, but
exactly.
Possibly.
But yeah, I don't know the way we're going. Maybe there's a good thing for the Earth. But anyways, moving on. So I'm not an anarchist. So what's interesting this week with regard to this supervolcanoes is we've known about this volcanic chain. It's basically a chain of volcanoes that sort of plot their way through sort of the side of Tasmania right up through Victoria, New South Wales, and Queensland, and sort of end up sort of around what do you reckon, around Cairns, sort of a little bit south of Cairns, in Queensland. Now somehow this story got past me last year when it came up, because we knew these volcanoes are there, but we didn't know prior to this point, prior to about September last year, that these volcanoes were actually part of a chain that was formed by a hotspot. A hotspot, like Hawaii, is another famous chain of islands, in this case formed by a hotspot. It's the Pacific Plate moving over a very large magma plume, and that, of course, causes this chain of islands. Well, it's a similar sort of process here, but of course in this case we've got a continental plate that's moving over a hotspot. And the hotspot's undoubtedly still there. In fact, they reckon it's somewhere off the, I think, northeast of Tasmania at the moment, just sort of hanging out, waiting to make something, maybe. But of course, the volcanoes themselves that are in this chain are extinct. Now, if geologists look at the rock that's in these volcanoes, they can see that they're related by the composition of the rock, by the chemical composition of the rock. They can say, okay, these are actually formed by the same source. So it's the same thing that's really led them to discover this temper tantrum throwing of rocks right across the continent, as they've discovered some rocks over on the west coast, over almost 2,500 kilometers away from what they know to have been a supervolcano eruption, sort of around the Whitsunday Islands off the coast of Queensland. So they've found these rocks that don't belong there. They're sand-sized zircon crystals, for those who are following, and they don't match up with any of the rocks that are found in this area of WA. But they do match these rocks in the Whitsunday area. So it means they've been chucked there by a temper tantrum-y volcano, which is really cool. Can you imagine? Where else there? I'm actually really keen now to know, so scientists, please get onto it, where else these rocks are in the world, because that will give us an idea of what the spread was when it erupted. Where else are these things?
Well, presumably you could just draw a circle around that 2,200 kilometre sort of...
Well, not necessarily, because there might be things
circle
like wind that are involved, and so on and so forth. What I'd be interested, I mean, these crystals that are found, although not very big, they're also not, dust. So how much dust would have been thrown up, and would it have affected Earth? This story mentions and this is something else that we were having a bit of a giggle about before, was the largest super eruption that is known. Although they say in the story on record, and Ed was saying, well, where is the record? Is it a cave painting? What is going on? But this was from the Toba volcano in Indonesia, and that was around 75,000 years ago. And for that particular volcano, there were sand sort of particles that were blown over a similar radius to this, just over 2,500 kilometres. So if that's the case, if our spread of these crystals and the supervolcano across the continental landmass of Australia is actually, if the volcano is in the centre of that, if it were, as you said, if you were to draw a circle around it, then we have something that's twice as wide, potentially. So this could have been significantly larger, but of course it really just depends on, winds and all that sort of stuff. So that's why I'm really keen to know is if they find some more evidence of these exact crystals elsewhere in the world, because it will help us to calculate what that spread actually was.
Sure. It's not all that surprising in some ways. I mean, we've seen volcanoes spew dust and ash huge distances. I mean, the 2010 Iceland volcano Eyjafjallajökull.
Oh man, I'm so impressed. You can say that. Say it again.
Eyjafjallajökull. It's probably not 100% right, and we're going to get all our Icelandic listeners emailing us in and complaining. And which
Hello,
is
Iceland.
Fine. Go for it.
Send us an audio file of how you actually say it. That would be awesome.
Go for it. But we've seen the distance then, and this was a plume that sort of was lasting for 2 weeks of just ash and dust being thrown into the air. And so you can imagine if that was also spreading for thousands of kilometres, it's just an extraordinary amount of power that they can deliver.
Yeah.
But the only question I guess I have about this is, how do we know that the rocks were definitely transported there by a volcanic eruption? Couldn't they have just been sort of on the surface and insects carried them that far or something? Or some really hardy Iron Man shrew just running around with it. I don't even know if we have shrews in Australia. Maybe we did back then. But my point is, we're assuming it's volcanoes, and that's probably the most obvious reason for it. But I'm wondering if there's any other possible explanations for it.
It's certainly not something the story addresses, but I guess maybe. Potentially, but hopefully they've considered these things. But mind you, I mean, that reminds me of the Tabby Star, discussion. I've seen a lot of, I've read a lot of media coverage of this and various, postulations as well.
This is the star with the Dyson sphere around it. the alien
That's
megastructure.
right. And so aliens. I've seen a lot of discussion of this, of what it could be, and I'm really a fan. Although I think it's so incredibly unlikely, but I'm such a fan of. There's something that's much closer to our star system that happens to be in between us and them, that's traveling towards us to kill us all. That's I reckon
wow.
that's
Okay, cool.
You're a fan.
Yeah, I'm a fan. I reckon that's, and I've not seen anyone else discuss it. So I'd like to know why. Why is this not being discussed? Is it a cover-up? Is it Trump? What's going on?
I was so going. This sounds conspiracy theorist, and then you went down there as well.
I went there.
Thank you for beating me to the punch.
I should say, I don't think it is that. I'm sure we'll figure it out eventually, but it would be really cool if we go, you know what, it just can't be anything else. We've eliminated everything else.
Well, I mean, what was the quote? That there are two possibilities: either we're not alone in the universe, or we are alone in the universe, and both of those are frightening.
Yeah, absolutely.
But anyway, we went from volcanoes to aliens. Well done.
In a heartbeat.
Well, let's continue our theme of ancient history, and let's talk about the origins of life. Now, the long-standing explanation has been the primordial soup theory. Life began in a warm puddle on the surface of the Earth, chemicals were reacting, they got struck by a lightning bolt, and then we had life. Or, one day God got bored and made an amoeba. But last month, a study was published in Nature Microbiology that suggests the first living cells were born deep in the ocean, in warm, rocky, hydrothermal vents. It's an idea that I've seen tossed around a little bit, but this is actually a fairly in-depth study of it, and it's got legs, hasn't it, Shane?
Well, not really, because they were bacteria.
Well, not legs. The theory has legs. It's a phrase. It's a figure.
You opened it up, and I had to say it.
This is what I have to work with.
Microbiologist joke.
Yeah, no, that was pretty crap, wasn't it? I do apologise.
Yeah. Well, because it kind of encroached on dad joke territory as well. So
I'm not even a dad, so what's my excuse? Anyway, as Ed said, this idea isn't actually new. It's been around for quite a while. In fact, one of the articles we found about this dates back to 2002. So the idea has been around, but it's always I think been considered a bit not crackpot exactly, but a bit left of field. And it's testament to how important the primordial soup theory has been for such a long time now. And on the face of it, it actually makes a lot of sense, because they have done studies in the past where they've shown that if you recreate the conditions of about that time back, I can't remember how many billion years it is, but we'll say very, very long time ago.
It was about 3 billion, I think.
3 billion, yeah. If you mimic that time, you can produce basic building blocks of life, like amino acids and things like that, which could lead to some sort of a replicating molecule that would be inherited, and therefore that's the precursor to our modern day DNA. And the idea is from there that life built slowly around these things. You had these repeating selfish molecules that then wanted to protect themselves, so they aggregated primitive kind of membranes, and life started from there. The problem with this theory is that the energy source required to keep powering this wouldn't have existed at the time. That's how I understand this, anyway.
Well, that's why lightning is the theory. That's what gave the spark.
That's what gave it the
life.
Spark. But then, how did that then get maintained? How where was the energy harvested from to keep those molecules going? Like, did they have to wait for another lightning strike to do this, or what? It's a little bit sort of it doesn't make a whole lot of sense when you think about it a bit too much. However, hydrothermal vents, which are these basically very deep in the ocean, where oxygen and light does not exist, it's from what I understand, and I'm not a geologist, so if I get it wrong, please forgive me. It's basically where, well, it's a hot vent, and superheated water comes up through these hot vents. What's important is the difference in pH between the water that comes from the inner Earth and out into the ocean has a different pH, and therefore that's a different proton gradient. And all life is dependent upon proton gradients across membranes. That's how we power everything. And what this article that that we'll have in the links is very good at explaining is life could have theoretically formed from all sorts of different energy sources and all sorts of different ways, but all life on Earth is based on this proton gradient idea, where you have a difference in concentration of protons between two membranes, and that difference basically makes protons go through a sort of a turbine in the cell membrane, and that drives energy.
Mm-hmm.
So the hydrothermal vent would have been the perfect place for this to be kickstarted, because obviously all cells do this naturally. They produce their own proton gradients, but how did it start? And if this is a geological thing, that could have kickstarted that first very primitive membrane to drive an energy force and start doing rudimentary cellular processes. So it's an interesting idea.
It is. It also makes me think, though, why would it have necessarily only happened once? Over a billion of years, you'd have thought that sort of thing could happen many times, and you could have multiple common ancestors of life, I guess. But we don't. I think we've all come from the one event, I think, is the current theory.
But I really hope it's happened multiple times, because that links in really well with the next story.
Yeah, but
well, we'll get to that. Don't jump the gun.
Lucas. Yeah. Well, I mean, the thing is that it could have happened multiple times, but I mean, for all we know, this form of life was the most successful.
Well, that's true. Yeah, it may have happened and died out. We'll never know about it.
Yeah, and there's a very obviously we only work with what the genes we have. I mean, this nature study it's sort of a meta study. Like as far as I understand, they try to figure out from what we know of prokaryotes from bacterial genomes now, what would have the first, what they call a LUCA, or last universal common ancestor of all cells, what that cell would have looked like. Yep. And they figured out from all their data number crunching that it would have been a very similar sort of bacterium that lives in these hydrothermal vents now, which, as far as I'm aware, sort of uses sulfides for an energy source, and i.e. not oxygen. So that sort of life would not have been. It would not have been possible to have this sort of life in a shallow pool in primordial Earth. It's just not possible. So it's quite probable that. Well, this theory has now been given a bit more of a kickstart. That it seems to be a little bit more likely than the shallow pool idea. So,
and it's also, like I said, it's been tossed around for a while, this idea, and I think the protein gradient thing that you were explaining, I think it's very hard to. Gradient. Yeah, what did I say?
Protein.
Okay, sorry. But that proton gradient thing it's very hard to explain in just audio, and I think the best explanation that I've seen given for it was Brian Cox, and I think it must have been Wonders of Life.
Of course it was Brian Cox.
Of course, we love him, and he's great at this sort of thing, but in Wonders of Life, when he's in a volcanic lake that has that high acidity, and he just demonstrates lots of graphics and everything to show that as the protons fall, and that's how this could have sparked life.
Well, I mean, what is interesting is that is the common that's the common sort of thing that we share with all life shares on Earth. It's that same that's what powers life.
Yeah.
So it does seem to suggest that our common ancestor all did that from the very start, and that's what we've inherited.
Very cool. And Lucas, you're dying to talk about this next story, I know, which is the speculation that one of NASA's ambitious plans could be facing serious financial cutbacks and possibly even cancellation. But let's start with talking about the Europa Clipper mission and what it is.
So this mission's been on the drawing board for quite a while, and I remember hearing about this, it must have been about 8 years or so ago, in terms of not necessarily this specific mission with this specific planned orbiter, but the fact that we really need to send something to Europa to investigate it more, because what we know of Europa is very tantalizing in terms of our search for life that is not here on this planet. Europa, as you've probably heard, many, many times before, Europa is probably one of the strongest candidates for life within our solar system, other than Earth, which is 100% confirmed, because it does appear that Europa has a subsurface ocean, as in not frozen water, moving water, liquid water, which is exciting because for a long time we thought that the so-called Goldilocks zone was really important for that, but the Goldilocks zone really relates to having liquid water at the surface where the atmospheric pressure is appropriate for the temperature range that's in play for the water to remain liquid. But surface pressure is something that actually has a big impact on when water moves between its states. And it just so happens that Earth is in the right temperature range, most of the planet at least, and has the right atmospheric pressure range to keep water in its liquid form, which is not the case really anywhere else in our solar system right now. But when you look at Europa, and we've since found there's lots of other moons that potentially fit into this a similar category. We've had sort of discussions of so-called slushy moons before, which other of the Galilean moons that around Jupiter appear to be of a similar makeup, which is also cool. But Europa's special because it's covered by a shell of ice, and we think this ice sits atop a very vast, liquid ocean, and potentially maybe there's a rocky core. It's in fact quite likely that there's a rocky core. If that's the case, then something like the previous story we were just talking about, where hydrothermal vents may have at least at some point been active, is quite likely because everything's in place, everything's there that we need as far as we know. At some point there's been heat inside of all of the rocky bodies, so it's just a part of their formation. So there would have been heat at some point. It's very likely that there were hydro vents, and therefore if it's now seeming quite feasible that life could in fact form, as in kickstart in that sort of environment, then Europa's even more likely to have life if it is elsewhere. In order to find that, we've got to go there. We've only been able to find out so much from previous missions. Juno's there now is not really going to give us much more about Europa. Unfortunately, it's not part of its mission. It's really giving us, we hope, some awesome stuff about Jupiter, and I'm sure we'll cover that later on in more detail as more comes in. But Europa still is kind of a tantalizing target, and this particular mission is designed to get us the next step there. It's not a lander. We're not putting anything on Europa to potentially melt through ice or drill through ice or anything like that. That, if it happens, will be further in the future. What this particular mission is designed to do is to give us more information around the structure of this ice. How thick is it? Are there magnetic fields? Where are the magnetic fields of Europa? Because that gives us indication of all sorts of other things as well. There's a whole lot of radar related things. There's mass spectrometers. There's all sorts of things that are designed specifically to give us what we lack about Europa in terms of planning future missions and what we might do to find life there. So it's an important mission if we consider life elsewhere to be important. And personally, this is one of the things I really hope I find out, while I'm still on Earth. That didn't come out right. You know what I mean?
Well, while you're still alive anyway.
I'm not going anywhere, as far as I'm aware. So yeah, I think it's really important, and I also think it's one of those things that if we do reach an answer that there is even microbial life elsewhere that has evolved elsewhere other than on this planet, I think it will have profound impacts upon the way that we see ourselves in the universe, and I really hope that we do find that. And as Ed said at the beginning, if we find that there's nothing there, I think that also will be very profound. So I think it's important. Now, the story that's come out this week has been suggestive, at least, that the funding for this mission, Europa Clipper, may be in doubt. And it's not quite as simple as this. It really comes down to the funding periods that NASA works to and its bids for funding versus what Congress and the Senate are prepared to give them. And at least for 2017, which is a fairly essential part of the lead up to the Clipper mission, which is meant to launch around 2022-ish or something, that it actually has all the instruments ready and the project is ready to launch at that time. It's certainly looking at the moment that there's some discrepancies between what NASA are asking for 2017 and what Congress has pledged and what Senate documents are indicating will be the case. It's quite significant difference, in fact, with those. But apparently that's not uncommon in itself, and usually things sort of even out. But it is looking that with NASA's bid of only about $50 million US dollars for this, that they're probably going to be putting this at least parts of this project on hiatus for that year, and that has roll-on effects. There's a lot of conjecture in this story.
A launch window isn't something you can easily delay. It's the sort of thing that has to be when the planets are at the right
That's
spot.
right. Orbital dynamics really dictates your time frames here. And this is a straight shot as well. This is, we're firing something directly at where Jupiter and Europa will be when it gets there. It's not something that's going to go on a meandering orbit slingshotting around things and stuff. There's no gravity assist with this particular shot. So yeah, you're right, exactly right. It has to launch when it launches. So it'll launch with the instruments that it has. And I just...
You go to Europa with the science instruments you've got, not the science instruments you want. It had to be done.
It may well be. I mean, they've certainly not pulled funding for it. And in fact, Congress are indicating that they've earmarked more funding from this than NASA's asking for. So it may just be that, NASA's jiggling around its priorities at the moment. And I'm hoping that's the case, because there's not a lot we can infer from this other than priorities may be changing. We know these things do take a long time to plan and build, especially something that's quite packed. I mean, this particular craft has got quite a lot of instruments on it. So yeah, I hope it doesn't get flipped.
I think part of the reason why we haven't sent anything to Europa before is also the fact that it's a really difficult moon to study, because Jupiter has such a huge radiation field. And so this is not even going to be orbiting Europa. It's going to be orbiting Jupiter just dipping into Europa every now and then.
Yep.
Because the radiation is so strong, anything's going to get fried. So you need to really develop good shielding for it. You need to design the craft in a way that they're not going to be exposed to the radiation for very long. It's a huge engineering challenge.
It is. You're dead right. And I assume there's a lot that they'll get out of the Juno mission, which will help, with the planning of this one, because it's exactly right. It is actually going to be an orbit around a very large sort of slingshotting orbit around Jupiter. It's projected to perform something like 45 or so flybys around Europa, and it will get down to, I think, as low as about 25 kilometers above the surface. So I mean, that's really close. If you're going to do 45 flybys, coming in that close is awesome, because it just gives you a huge amount of potential that you wouldn't have, particularly with mass spec and that sort of thing. So and radar indeed. So yeah, we'll see. We'll really see. But I just hope this one doesn't get shelved, because this is one of the ones that I've been hanging out for most of my adult life to and I know it's not about me. I know. But I really want this one to go ahead, and then everything that happens after it, because otherwise it'll happen when I'm dead. I don't want that to happen.
All you got to do then is make sure you live a lot longer. So work on that.
Yeah, great.
Which is a interesting note to end on. For more information about the stories we talked about, check out the website, scienceontop.com/239. Leave us a comment, get in touch with us on social media, send us an email, feedback@scienceontop.com. And as always, we really appreciate the reviews you leave on iTunes. Thank you, Shane and Lucas.
Thanks, mate.
No worries.
And thank you, everyone, for listening. We'll be back again next week, putting science on top of the agenda. Join us then.
Facebook. It's hard to imagine a world without it, unless you're me. Rob Schneider has 260,000 fans. Nickelback, almost 19 million. Chicken Nuggets, 179,000. And the CSIRO, a measly 85,000. Are you saying you like processed chicken in the shape of a boot more than you do Cyro? Have you no shame? Cyro gave the world plastic banknotes, 3D printed sternums, the total well-being diet, AeroGuard, Wi-Fi, you know, the thing you're probably using right now. Hell, they even invented the word for the smell of approaching rain. Have you ever used it? Probably not, but it's petrichor, and it's awesome. If you're on the first date, use it.